In the title of this video, you'll notice a word that you probably haven't seen before, vibronic. Let me define what that means, and then we'll discuss what its implications are for polyatomic molecules. A vibronic transition is one that involves transitions in both the electronic state and the vibrational state at the same time. Now we've seen a good example of this before in diatomics, and I'll remind you that when you have a diatomic molecule and it goes from one state to another state, and we start down here typically in the ground state of the lower oscillator, it makes a transition up here, and we can actually see a progression of vibrational lines that correspond to the locations of the energy eigenstates on the upper potential surface. That is, we've made an electronic transition from the ground electronic surface to an excited electronic surface, and in the process of making that transition, we actually see a progression of lines in the vibration. So the spectrum for this might look something like this, where we've got a whole series of bumps along here, and each bump is a different vibrational state corresponding to the vibrational levels of the upper electronic state. All right, this is something that we refer to as a Franck-Condon progression, because this whole idea of the molecule making a very quick and abrupt transition up here so that it doesn't move, the nuclei don't move during the course of the transition, is something known as the Franck-Condon principle. And I'll remind you that, in fact, the probability for making this transition from one state 0 to another state 1 is proportional to the square of the overlap between the initial wave function. So this is the ground vibrational state and the ground electronic state, with the first excited electronic state and some number or some set of vibrational states on that state. All right, so this is the Franck-Condon factor that tells us about the relative intensities of these various transitions that one might make. So it would tell us about the relative heights of these peaks in this progression. Okay, so this was the diatomic case. Do we see something similar in the case of polyatomics? Well, we actually do. But what I want to do is draw a more generalized picture here, and I hope you'll give me a chance to exercise some artistic license here. Now you'll notice that I'm purposely drawing these states so that they have, this one's a thin potential and this one's a thicker, a broader potential, because I want to have a very thin localized state that I'm starting in down here. So here's my initial state down here, and it's going to be lifted vertically up here. Okay, but as I've drawn it the same as I have over here. But what's different in a polyatomic molecule? Well, what's different is there's more than one vibration. So let's just make a second vibration, okay? It doesn't have to be anything fancy. But if I had a second vibration, I can imagine this not being some narrow, that is flat as the paper sort of potential, but now one that has another dimension. So this is more like a bowl. Okay, I hope you can visualize this as a bowl, and I would similarly have a bowl up here. All right, I haven't drawn this very well, but I hope you can see that there's a bowl up here and a bowl down here, and these bowls are different width. All right, now maybe a better way to visualize this would be if I were to draw a contour map of this upper potential. What would a contour map look like? Well, if I were somehow able to look straight down into this potential, and there were level lines at different places on there, I might see a set of level lines that looked like this. Now I've purposely drawn these with different dimensions because I want to emphasize that I have a wide coordinate here and a thin coordinate here. All right, now the wide coordinate is basically going to be one that has a lower frequency of oscillation. The narrow coordinate will be one will have a higher frequency of vibration. Now where this comes up, where this particular state ends up here, for example, could be localized, say, right here. So in other words, it is displaced in both of these two coordinates relative to the minimum of this surface up here. This would be the minimum down here. All right, so it's displaced in both of these coordinates. So if I were to somehow draw a cross-section, so let's draw this cross-section. And sorry, a lot of drawings here, but I hope they make sense. If I draw this cross-section, so it's going to be some broad harmonic oscillator here. And since it's a low frequency, the states are going to be relatively close together. Remember, the frequency is what determines the spacing between the peaks. So if it's a low frequency, if it's a small frequency, the various energy levels will be closer together. And so our initial state up here is now going to be something that is, located over on the edge, just as it was here in the diatomic case. All right, so it's going to go back and forth here. It's going to reflect a progression in this set of narrowly spaced harmonic oscillator lines. So I'll just say it will be a dense progression. It will have a lot of lines in that progression, and I'll draw it in just a moment. What about the other degree of freedom? What about the other vibration? Well, this one is a little bit narrower, like this. Since it's a narrow one, its energy levels are going to be farther apart. And when we draw our initial state on here, it'll be something like this, and it'll be overlapping the various harmonic oscillator eigenstates here in this part of the surface. All right, now this is one that has as I said, higher frequency, so it's not going to have as many states in it, so it's going to be a less dense progression. We aren't going to see as many of these energy levels. Now, whenever we have a case like this, and I've drawn it as though we are actually in normal mode, so these two harmonic oscillators are more or less distinct and separated from one another, they're not coupled together, that means that we can write energy levels down for each of them. So for example, in the first case, I'll have an energy that's a function of E1, and that would just be h bar omega 1 times n1 plus a half. For the second one, I'll have an energy level as a function of n2, h bar omega 2, n2 plus 1 half. Okay, so what I'm saying here is that we have two different frequencies, and each of these different degrees of freedom, these different vibrations, have their own quantum number. And so in order to get the total vibrational state for this system, I need to add these up. So the vibrational energy in this case will be h bar omega 1 times n1 plus a half plus h bar omega 2 times n2 plus a half. All right, so how does this manifest itself in the progression? Well, when we take an electronic spectrum, a vibronic spectrum, what we're seeing are the energy levels for this upper state. So I should be pointing to this one. We're seeing the energy levels of this state. So we're basically detecting all of these. Now, my hypothesis was that this one was going to be a low frequency. So this is a small number, and this is a large number. So let me draw the large one first. What I'm going to do is sort of map out where I would expect to see lines here. Okay, so this will be our relative intensity, although I'm not really going to draw the intensity here. Okay, I've got widely spaced lines here, and these all will correspond to n1 equals 0. Okay, so I'll have one here which represents sort of the origin of the whole spectrum. Call that E00. Both quantum numbers are equal to 0. And it's down there. Now, this is a larger frequency, so it's going to have spacings that are somewhat broader. So this would be E01, and this would be E02. Now, what about the other progressions here. Now I'm hypothesizing that these now are small frequencies, so they're closer together. So I'm going to draw these in red, at least this first one in red. So I'll have a set of lines, say one here, one here, one here, one here, and so forth. And you'll notice that they don't match up necessarily with the location of E1, E01. All right, now I want to draw what happens when I start with N1 equal to 1. Actually, sorry, this is N2 equal to 1. Okay, when I build a progression off of this, the spacing between adjacent lines will be the same as it was for the last one. I'm going to draw these in purple, but I'll have a line here, a line here, a line here. And so forth. Okay, finally, when I begin building lines off of E2, and I'm going to make these in green just for some contrast, and I'll make them even taller so we can see them. I'll have lines here, 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 and here. So what we see is I have progressions in two different vibrations. It will appear as a series of peaks built upon different numbers of quanta in the higher frequency oscillation. So I have a series of peaks here, a series of peaks here, and a series of peaks up here that would go on as well. So this is the sort of thing that you would see in a vibronic spectrum if there's more than one vibration that's been activated. Now the whole reason for going through this is to get you to think about the fact that polyatomic molecules have many vibrations, many normal modes, and all of them, or none of them, or some of them can be activated by an electronic transition. It really depends upon the shape of the electronic potential energy surface, the one that is at the heart of each of these electronic states here and here. The initial state here only determines, in some sense, what the relative intensities are going to be through the Franck-Condon factor that's given here. All right, but this set of progressions is something that you see often in larger molecules. It is something that gets washed out if the molecules happen to be in solution or in some sort of dense gas phase where they're having lots of collisions. That can cause these things to run together. But if you're able to isolate them in a molecular beam, for example, you could see individual lines for each of these progressions, and really a beautiful display of the Franck-Condon principle at work.